right, hello everyone. Thank you for joining us. My name's Austin Smith, Business Development Executive for the Innovation and Partnerships Office at Lawrence Livermore National Lab. We're excited to be participating with the Department of Energy's Office of Technology Commercialization National Lab Discovery Series to bring you our recent breakthroughs in massively parallel two-photon lithography using meta-optics. Before I introduce our speaker today, I wanted to take a few minutes to share a little about LL&L, highlight a few facilities and capabilities unique to our lab, and share how you can partner with a national lab like us on technologies such as this two-photon lithography. So we're part of the Department of Energy's 17 national laboratories that are providing large-scale multidisciplinary capabilities and unique facilities that are among the leading institutions for scientific innovation. For more than 70 years, our national labs have been the leading U.S. institutions for scientific innovation, translating basic science into scientific innovation and meeting challenges that are not met by universities or commercial resources. We sit in a complex along with two other of the NNSA labs that have a really strong emphasis on multi-purpose national security. So our mission to strengthen national security through world-class science, technology, and engineering really defines where our lab truly excels, from multi-domain deterrence and stockpile stewardship to world-class applied sciences, engineering, and unmatched high-performance computing. Our unique facilities highlight our capabilities, from the National Ignition Facility, the largest and most energetic laser facility ever built, where we've demonstrated record fusion energy yield at 8.6 megajoules, more than 4 times what we applied to our target chamber, to our computing complex that houses El Capitan, the world's fastest supercomputer, at 1.74 teraflops. Our facilities cover everything from biosecurity, energetics, metrology, and extensive capabilities in both micro and nanotechnologies. Our work today is featured from the Center for Engineered Materials Manufacturing, or CEM, which serves as an innovator and keeper of these core capabilities that you're going to see today. So from multi-scale modeling and simulation, all the way up through digital twins, AI, and machine learning. I help represent the Innovation and Partnerships Office, which helps support the execution of agreements like NDAs and CRADAs, along with licensing of technologies that are developed here at LL&L. We also support our scientists and engineers with entrepreneurial training and business development to help our principal investigators connect with partners outside of our square mile. IPO's activities centralize our efforts in technology transfer that enhance our mission capabilities as a national lab and increase return on R&D investment. They enable economic growth and development while securing U.S. economic and scientific competitiveness in a rapidly changing world. Our team thinks of technology transfer as a journey where we help guide outside organizations, starting with introductions and mutual assessments. Between our individual groups, we proceed through a discovery stage where we may execute NDAs, MTAs, and the like, and further discuss areas of mutual interest. We'll define a collaborative scope of work, identify deliverables and resources that are necessary to execute that work, and translate our technology into an industrial solution that matters for you. When we can provide security to your business through intellectual property or add value through partnering, sharing our know-how, these are the areas where we think we can really have an impact and help make a difference for you. Our team has several focus areas for commercialization. Today's topic is really going to focus on 3D printing and advanced manufacturing techniques that are well positioned for impacts in electronics, optics, and life sciences. And lastly, I would just say that our technologies have driven billions in economic impact, including over $750 million in products that were sold based on our technology just in the last 5 years. in a couple of these areas highlighted on this slide. We've had 4 public companies that have been started by LL&L scientists that have a total market value now of more than $20 billion. And with that, I'll go ahead and introduce Xiaojing and the main title of our talk.
All right. So thank you everybody for joining today. I'll start the technical section of the talk. So just to give a little bit background about two-photon lithography, it is the highest resolution 3D printing technique on the market today. So if you look at this image, Edward Teller, he's the founder, one of the founders of our lab, and we have here it's Mario Goldberg-Mayer. She got Nobel Prize for discovering two-photon absorption phenomena. So we're using this for 3D printing. So if you look at here, the 2 images in the bottom, we have objective that is focusing the light into a tight spot. And if you have single photon excitation, the whole beam path is excited. This is why traditional lithography generally is a 2D process. If you leverage 2 photon excitation, we're using 800 nanometer laser, and the resin, the liquid resin, is only sensitive to 400 nanometer of light. So only at the focal spot you can have enough photon flux to trigger a 2 photon absorbing process. So you're curing that liquid polymer resin into a solid polymer. So if you move this spot in 3D, we can draw out any 3D geometry with very high nonlinear threshold that is very accurate. So this method is particularly good for making very fine nanostructure or microstructure architecture, such as foam structures with tailored design and bespoke properties. And as you can see in the video, that we have very fine pen tip, and we need to draw out 3D geometry, and it takes a very long time. So the key drawback of this method traditionally is the slow printing speed, and this is what we have been working on to solve. So this technique has been used in academia research for a very long time. So being able to control that material architecture at the nano and micro scale really enable a lot of breakthrough performance and novel functionalities in a lot of research areas. For example, in mechanical structures, we can make very lightweight and strong and resilient material. In terms of metamaterial, we can control the light and acoustic wave propagation by designing the structures. My PhD background is in electrochemistry, so we're able to engineer 3D printed batteries that can control the reaction diffusion of the battery chemistry very accurately and very efficiently. So people have also made microfluidic devices and MEMS devices that have very interesting properties and high performance. However, as you can see, those images, they're all SEM images. They're very small, a few hundred micron in size. But for actually real life deployment of those applications, we need larger scale samples. We need to be able to make them much faster. So this is a big bottleneck moving forward. And also, if you notice, all of the structure are either periodic or we need a large array of them. So we will be taking advantage of that. And so for our previous printing effort, the community has been focusing on the optical beam paths. So there have been ways to improve the printing speed by using a lot of interesting optical techniques. But in the end, the light goes through a high numerical capture microscope objective that have a field of view of a few hundred microns. So you can print fast within a very small area, and then you have to print a small section and then stitch another section next to it. So about 6 years ago, we started to ask the question, what if we can make a large lens array? So we can have a more powerful laser go through that lens array, and we can generate thousands or millions of focal spots in parallel. And each focal spot will print the same structure. And if each lens prints the same size of structure as the lens itself, we can have a connected architecture that have very fine feature, but also very large size. So this is actually a paradigm shift from previously, we're always scaling down within the field of view of a microscope objective. Now we hope to scale up towards a wafer scale. So the first question we ask ourselves is, are there laser that is powerful enough? The answer is yes. We actually have a pretty old laser, 10 years old laser, that is amplified femtosecond laser. Individual pulse energy is actually 1 million times stronger than the traditional laser that used in two-photon printing system. So we have laser that enable us to achieve large degree polarization. However, the replication rate of that laser is slower, so that we have to move slower when we print 3D structure. But overall, we can still have the potential to have more than 1,000 times printing speed enhancement by using this parallelization scheme. So what type of lens can we use to make this happen? So we're looking into meta-lens. So meta-lens or meta-surface are carefully engineered structure. They are sub-wavelength refractive dielectric material. In our case, we use silicon, and it's very good for the 800 nanometer of light that we use. So depending on the geometry or size of this nanostructure, you can control the phase and even the polarization of light. So this is a different regime compared to traditional optics. We're using the curvature of the refractive media to control the light. So now if you carefully arrange those nanostructure building blocks at different locations of a device, you can make very high performance optical system. For example, high numeric capture lenses have been made for a very long time. And this technique is also compatible with wafer clean room fabrication, so you can make a large array of these lenses on the same wafer, and silicon is one of the material that can be engineered very accurately in the clean room fab space. And we also have very systematic inverse design method that we collaborate with Stanford University, so that given a specific lens requirement, we can design the nanostructure systematically to enable us to achieve the optical property. So here is the overall schematic of our system. So we have amplified femtosecond laser that is controlled by a spatial light modulator that I will talk a little bit more about later, that eventually go to the meta-lens array, generate many focal spots. And in the bottom, we have a motion stage. That motion stage will move in 3D and prescribe that 3D geometry during the printing process. And here is an example of our final product. So you can see here, we have a very intricate micro lattice structure, and this box is printed with one metal lens. The box is 200 micron in size. And because we have a large array of those metal lenses where printing structures next to each other, they will be stitched together in one process automatically. And the minimum feature we can print using this method is a 113 nanometer line width. And this technology, last year, it just won the R&D 100 award. And so I won't go into the details of the optical setup, but essentially, we are using a spatial light modulator that enables us to control every single focal spot. And in our system, we have 120,000 meta lenses. And each of the meta lenses is controlled by an array of pixels on a spatial light modulator, so that we can first make them extremely uniform. That is the fundamental basis for being able to print accurately. On top of that, each focal spot pretty much acts as a miniature printer in itself. So we can really have very high resolution, and we can, by changing the illumination condition, we can also change the line width of our printing. And each lens is either 100 or 200 micron in size. So within that size, we can print any geometry through mechanical motion. So really free form fabrication. And all together, we have a very large write field and with a very high throughput. So our current printing speed, using 120,000 meta lenses, we can print about 1,000 times faster than commercial off-the-shelf printer that have only one focal spot. And so here you can see that our printing area is about 3 centimeter by 3 centimeter. The size of printing area is 5 order of magnitude higher than the resolution of our printing technique. And here, Dr. Song-Yin Gu is showing our first large area print. And this print would have taken a few months on commercial printer, and it's only taking us 2 hours to print. And so this technique is naturally suited for making replicas, or many, many replicas of a microstructure. Here I show a few examples, and those structures you can see they are unmoldable. They're microstructures that can be used for example, drug delivery, but you can never make them in ways that is not additive manufacturing. So our printing throughput enables us to print 50 million of microparticles a day for future application. And we also demonstrate a few kind of micro functional material micro devices, such as multiplex neural probe array, so we can probe different depths of neural cortea using this type of 3D geometry design. So they are continuously connected by stochastic foam that can be used for absorption or filtering purposes. We also made a terahertz metamaterial. You can see the helix, the handiness of those helix will control the polarization of terahertz wave. And so, but we're not satisfied with printing only periodic structures. So one common use case is that we need periodic inner microstructure that can control the property material, but overall we need to have an exterior boundary that can be fit, connect to another devices, or have specific geometry for actual practical deployment. So in this case, because we have a spatial light modulator, we can actually turn off a subset of metallins so that we can print very intricate structure with exterior boundary that is controlled by our spatial light modulator mask. So if we take a step further, we can actually have different patterns on the spatial light modulator to illuminate different focus balls, and at those focus balls, we can print different patterns. For example, we can print like a simple cubic lattice in some places. We can add some diagonal tracks. We can add some walls in different locations. Here is an example of 3 different types of geometries that are combined into one architecture, and we made a demonstration of a microfluidic devices. You can see here we have 2 types of liquid that is applied into different locations of the sample, and they will be drawn into the capillary networks of the sample to combine and to run some chemical reaction. So this is an example that we can showing the benefit of combining different lattice geometry into a overall architecture. And but we're not satisfied with that either. So we want to really generalize our printing system. Here you are seeing a microscopic chest opening. Each chest piece is about 200 micron in size, and that is printed by 1 metal lens. So pretty much each metal lens is printing a different chest piece. And we do it by comparing the commonality between all the metal lens prints. For example, if you want to print 0 and 1 using 2 lenses, in the middle is the shared feature of 0 and 1. We turn both lenses on, and we want to print them in parallel. And there's also individual features of 0, individual features 1, that we turn individual lenses on to print that specific feature. We actually printed 16 of those chess pieces in parallel using this adaptive modulation method. You can see all the chess pieces shown in the video here. And we also generalize this algorithm into a way that we can essentially compare, we can subdivide the structure into substructures, and we can compare the target print across all focus balls to see what features are shared between what subset of focus ball. So we can turn those focus balls on and print the shared features, and turn another focus ball on to print another set of shared features. So overall, this is a compression algorithm. So for any arbitrary 3D geometry, we can compress geometry into a basis of focus ball. So that enable us to print even fully pure random structure, stochastic structure, still with a very large degree of polarization. So to demonstrate the functionality, we did some functional demonstrations. So here we printed what we call mechanical metamaterial. So those are little coupons of material that is 1 centimeter and 0.5 centimeter in size. And in the middle, we have a prefab notch for a very rigorous mechanical measurement. And you can see that the material is looks like a white foam because it have a very fine structure that scatters light. But if you zoom in, you can see it's made out of very small unit cells. So we have 3 types of different geometry of unit cell, and each sample is made from 240,000 unit cells. So this is very similar to how crystal structure of traditional material determine its properties. Over here, we have metamaterial that the inner unit cell geometry controls the mechanical property. If you look at the stress strain curve, we can see the 3 different unit cells behave very differently when they're under uniaxial tension experiments. So you can have, I'm going to show you a video of a more detailed comparison of those mechanical behavior. So in the bottom and top, I'm showing 2 videos of 2 different lattice types. They're under uniaxial tension. And on the top, we have an octet lattice that is really stretching dominated. It's very stiff, but it's very brittle. And so we can see a catastrophic failure. In the bottom, I have a Kelvin lattice. It's more bending dominated architecture. So it is less, have a lower modulus, but it have higher fracture energy. So it's tougher. It takes more energy to propagate that crack as we stretch the sample. And we also have a third geometry that is a chainmail lattice. This is very different from all the other lattice in a sense that those individual building blocks actually interlocked with each other. So it shows very interesting behavior as we uniaxially kind of stretch it. So each individual unit have a lot of degree of freedom to rearrange. So it can withstand extended elongation between fractures start to happen. And when it happens, it propagates very slowly. And we have very high energy of fracturing. So we did very kind of detailed modeling of this behavior. You can see that there's 2 chains of units that actually are load-bearing units. So when one chain is fractured, have breakage, the load actually shifted to the other side of the crack tip, and the other side will hold the load and then fracture next. So we have a kind of alternating breakage at two sides of the notch. And this is really fundamentally new mechanical behavior that is controlled by the local microstructure. And such structure, because they are very interlocked, it's really hard to manufacture using other methods. So parallel two-photon printing enable us to make those new structures and control very intriguing fracture behavior. And so this type of chemoelectric is actually a subset of what we call polycatenated architect material. So those are interlocked but not rigid connected units. And we last year we reported the design framework on the cover of Science with our collaborator from Caltech. And so now going back to our printing system, so if we put our printing system in comparison with all the previous published papers on this plot, where we have printing speed in the y-axis and resolution in the x-axis, you can see we're at the leading frontier, but unfortunately we didn't break the record. And however, we think this plot actually have a third dimension in it. If you look at here, so the right field is the area of writing that we can do simultaneously. It's another very important factor. If you plot all the point in this 3D space, you can see that all the previous results are very clustered in this very tight space because they're limited by the field of view of the objective. So the problem with that is it's really hard to continue to improve the printing speed. So if you put more energy or more information into that very tight space, you start to have proximity effect. That is a very common feature in lithography, where the chemical reaction will start to interfere with each other. And the fact that we're bounded by the field of view also take a toll in terms of printing speed, because for a centimeter scale, a larger sample, you have to print hundreds of thousands of individual prints and stitch them together. So you have a very large overhead of mechanical motion between individual subprint, and how do you stitch them together, and also between each stitching, there's certain inaccuracy, and you're accumulating a lot of error over time on a larger area print. And in our case, because we're printing at a very large area directly, so our scaling path is unhindered at the moment. So with off-the-shelf commercial upgrades of lasers or motion stages, we are quite confident that we can have another 2 orders of magnitude enhancement in printing speed. So now, with those very exciting 3D printing technique, I want to talk a little bit more about what kind of application that we can do using those the Metalens TPL method. So we're looking into 2 types of application space. The first one is that you want to make very complex micro devices, and you want to make many of them, volume production. And the second type of application is that we want to microarchitecture that are connected to each other. So we want to make a larger device that have many units in it. So I will go through 2 exemplars of those applications. I'll start from the first one. So as Austin mentioned earlier, so Lawrence Livermore have the National Ignition Facility. So about 3 years ago, we'll demonstrate historic scientific break-even in terms of fusion reaction. So which means that in this target level, we get more fusion energy out than we put in as a laser energy. And the next step is to have a facility break-even so that the whole facility can generate more energy than the energy input of the facility. And in the future, if we want to utilize fusion energy, specific inertial fusion energy that is laser-driven for energy to powering a small city or something like that, we need to have a power plant that is rep-rated. So that estimated shows that we need to operate the power plant at 10 hertz. So that means that we need to consume a lot of targets that need to be manufactured with very high precision. So today, the target is very intricate. It's one of the most perfect material we can make by human. So we start from a gold horum that takes about a week to machine. And on the inside of the horum, there's a capsule that's made of diamond that it needs to be polished to perfection. That takes about a few months to polish. So once we have this target, we actually have to grow a layer of deuterium tritium ice on the inside of this capsule. It's a single crystal layer of ice on the inside of the capsule. You can imagine it's really hard to grow kind of a solid hydrogen on the inside of a capsule. So it actually takes about a week of operation time on site of NIF to do that. So you have gold, you have diamond and crystal. My 5-year-old son really likes those, but those are very expensive material. So for each experiment, the implosion experiment, the target fabrication cost is about $100,000, which is okay for research. However, if we want to make a power plant, we are expected to have 5,000 capsules a day, and each capsule needs to be cheaper than 50 cents. So there's a big gap to bridge, and we think 3D printing can help with that. So why do we want to 3D print fusion target? So it's fast, it's flexible, we can change the design very quickly. The material cost of printing acrylic polymer is very low. And the biggest selling point, actually, we can print the inner foam layer together as we print the target, such that liquid deuterium and tritium can wet into that foam layer by capillary action. So this really simplifies the layering process. It's a process where we put the nuclear fuel inside the capsule in a very symmetric fashion. Otherwise, it's really difficult to do through the beta layering process. So by liquid wetting process, this can be very streamlined and can be done in batch processing. So we can also control the physics of by controlling the geometry of the capsule, essentially freeform. So overall, 3D printing have a lot of potential for future fusion applications. I have to mention that currently our target is not as perfect as traditional NIF target that we have demonstrated break even. There's still a long way to go. They are already very nice. So we're able to do a few fusion experiments in the last few years. So here is an example of our 3D printed target, and we coat some metal layer to reduce the preheat, and also build it into a full target. And we're able to demonstrate fusion reactions. So those are the first ever wet foam capsule and a direct drive that I ever shot on NIF, and we made that happen by 3D printing the target. And so far those experiments are kind of benchmarking experiment. They're at a lower energy level, and we're increasingly to understand our physics more and able to improve our target design to continue to push the boundary further. And I cannot think of a better way to destroy our sample through other than thermonuclear fusion reactions. So in the future, I think parallel 3D printing can really make mass produce those targets for future fusion energy generation. So another type of application is for quantum computing. So currently, there's a lot of interesting news on quantum computing, but for quantum computer to be actually useful in the future, we need to have thousands or tens of thousands to 1 million cubic so that we can run very complex algorithms like Shor's algorithm on quantum computer, and that requires new fabrication techniques. So the type of quantum computer chips we're looking at is called trapped ion quantum computing. We're using a trapped ion, in our case, a calcium ion, as a cubic for quantum computation. So traditionally, the physics community uses something called Paul traps. So those are macroscopic 3D electrode structures that you can apply your oscillating potential and trap a calcium ion or other ions in the middle of this 3D trap. And the community, this industry have really taken off in the last 20 years when people started to use MEMS fabrication technology to make surface trap. So those are surface electrodes, but if you're carefully designed them, you can have a little shallow potential well to trap ion. And the benefit of doing so is that it's very scalable. So MEMS foundry can make very accurately large array of those traps so you can use them for quantum computing. So our 3D printing technique actually combines the benefit of having a 3D geometry, so we can have very nice potential well to trap the ion. It's very scalable that each trap is also it's microscopic. We're able to make many of them in the future on the same wafer. So if you look at our potential well, you can see that our 3D trap have very deep and harmonic potential well. You can imagine a little ball oscillating in this potential well, whereas surface trap have very anharmonic potential well that is really suspect to errors. So because of our very nice potential, we're able to trap ions at a frequency that is higher than traditional surface trap, about 5 times higher. This means that you can actually compute at 5 times faster speed. And so I won't go into details of the quantum physics here, but we demonstrated single cubic and 2 cubic operations with high fidelity. So I do want to mention, we demonstrated using very minimal cooling overhead. So in this case, we have to trap an ion. We actually use laser to cool it down into ground state so that it can function as a quantum bit. And traditionally, this cooling process needs to have a Doppler cooling and sideband cooling iteratively. It takes a very long time to actually prepare the ion. So the most of the overhead is actually preparing the ion to the ground state for quantum operations. So we actually, because our very nice 3D geometry, we're able to get away with only Doppler cooling that really reduce the ion preparation time by a lot. So in the future, this is a very efficient way to produce ions for quantum computing, trapped ions for quantum computing. And so on the manufacturing side, so we're not only printing the trap itself, we also print out the electrical connects in one process. So this process takes about 14 hours to print each quantum circuit, essentially. And we can finish, we do one-step metal coating because we have printed some shadow masking feature such that if we do one-step metal coating, all the electrical connection actually isolated from each other, we can address the electrode individually. So each iteration process only takes 2 days. This is drastically faster than traditional foundry fabrication method that enable us to really rapidly prototype our designs. So we go from just miniaturization with microscopic design, where it's starting to evolve some very kind of interesting that that's only enabled by 3D printing to further optimize our performance. And once we have settled down on design, we can use a hybrid manufacturing approach to make this process faster. We can prefab pattern substrate such that we only need to print a 3D geometry on top of the pattern substrate. That really reserve, I think in the future, we should reserve 3D printing only to the geometry that is need to be 3D. And this will further improve the printing speed and increase the yield of our fabrication process. So now we are ready to try to build a large quantum processor, and which is very difficult. So the trapped community using this architecture called quantum CCD architecture. So it's a large wafer that have different zones, and you have to shadow the ion to different zones for different operation, similar to a computer chip. And we have proposed a 3D QCCD architecture that are able to do this very efficiently. And we're currently testing kind of horizontal trap designs that enable us to shadow ions and trap multiple ions. So imagine if you want to further build it into a large-scale quantum processor, our parallel 3D printing method can actually make many of building blocks in parallel, enable us to make a much larger scale quantum processor. So now I've gone through the 2 application cases: the quantum target, fusion target, which is you need replica of many identical structure, or the quantum trapped ion architecture, where you need modular microstructure that are connected to each other. So I will take a step back, talk about how materials are discovered and developed. So at the very bottom level, you have atomic structure that controls the crystal structure of the material. And then a level up, we have chemical formula. We look at the molecules, or how they are designed to have different functionality and properties. And for a lot of advanced material, people are using composite. So that combines different material property from different constituent material. So in the last 20, 30 years, 3D printing is starting to make a new concept called what we call architect material. So those are mostly additive manufactured material that local geometry is designed to have certain property. So we can really have much better control knob of material property here. And the community have a lot of very exciting papers in the community, but most of the time the structure are quite small. It's hard to use it in real application. And so I think the 2-photon metal-space 2-photon parallel platform can really enable us to transit from lab scale exploration into wafer scale production. For example, if we want to build a future, interconnect for heterogeneous integration or like advanced packaging, we can design a 3D structure that has thermal, mechanical, electrical, optical, or RF properties in one framework. And the parallel 3D printing can really enable us to make it happen and to be able to produce that structures with high throughput and low cost in the future. And so here, I want to acknowledge my team that at Livermore who have been working very hard in those printing platform and also develop applications, and also my collaborator from Stanford, from Caltech, and from Berkeley on very exciting academic collaborations, and also my funding source that are internal to Livermore from the UC Office of President and from Department of Energy. So now I'll give it back to Austin to talk about partnership opportunities.
Thanks, Xiaojing. Yeah, just real quick as a note for you attendees, if you do have any questions, whether or not it's on the technical side or they happen to be on partnerships, working with the lab, you'll notice at the top of your screen you'll have a little Q&A. If you click on that and go ahead and type your question in, we'll have a nice list of them. So as we sort of wrap up the main part of the presentation here, we can get a couple of those going. So go ahead and start thinking about that now. It's a great time to ask us directly if you have any questions about the science, the engineering, right, or fields of application. We're happy to get into it. But before I get to the Q&A section of our talk, I just wanted to briefly mention what we do have in the way of 2-photon lithography intellectual property that's available to license. So I've highlighted in gold on this slide the areas where we have either issued or filed patents that are working their way through right now that are, most of the fields of use remain open for licensing. We also have some other related intellectual property that could be relevant for your applications, whether or not we're talking about utilizing cationic polymerizations for orthogonal printing techniques, right, or utilizing different wavelengths to control what we're initiating in our vat of photopolymer, right? So in terms of our actual metal lens printing system, like you've seen here, this platform technology is available for licensing in most fields, with our preference to license non-exclusively or with exclusive terms that are bound by clear fields of use. Any licensing that's done through LL&L does require a valid commercialization plan to be submitted to us. We really do want you to use this technology and actually get it into industry. And IPO can help establish any non-disclosure agreements if necessary for technical discussions. So if we can't answer your questions today, we'll be happy to get that agreement in place so we can. And then just in terms of agreements for collaboration, these are sort of the main principal mechanisms that we rely on here at the lab. I just discussed commercial licenses, right? So these can grant rights to LL&L intellectual property that can provide you with an opportunity to commercialize and monetize our technology. We do have cooperative research and development agreements, or CRADAs, that are available, where industry partners provide research funds or in-kind cost contributions to engage in collaborative research, much like you would in industry with a joint development agreement, with the end goal of trying to commercialize LL&L developed technology for your application space. So it's firmly a collaborative type of agreement. And in this agreement, we handle things that can potentially provide access to facilities, most certainly our know-how here, and otherwise find a way to work closely to develop this technology to meet your use case. We also have strategic partnership projects where industry fund research efforts here, accessing our unique expertise. And this is really the laboratory's version of a work-for-hire type arrangement. You ask for a specific deliverable, and then we provide it. And in terms of contacting us for partnerships and licensing, I recommend our web portal for IPO at llnl.gov. We have a lot of other technologies that are available for licensing and partnerships. You'll find information up there about the technologies that Xiaojing has discussed today. And that's, I think, everything that we've got in the main part of our slide, and open it up for the Q&A section. Thanks, Xiaojing. And let's see. Just going through the Q&A real quick. So let me see if you can see this, Xiaojing. If not, I can read it out for you.
Yeah, I think it's better if you read it out so everybody can hear it.
No problem. All right. So I have one here. Thank you for the talk. How does the throughput print speed for fully aperiodic structures compare to throughput for fully periodic structures?
Right. This is a great question. So definitely this technique is most optimal and have high throughput when you're printing periodic structure. And if we're printing aperiodic structure, I think the scaling is actually very interesting as well. So actually, the more focal spot we have and the more complex the geometry there is, we're able to compress them better. So it's very similar to computer compression algorithm. So in the extreme case, the scaling, we detailed in our paper that the scaling almost behave as the relative density of the structure. So say if we're printing a foam or printing geometry that's about 25% dense, and the essential scaling in the end is that with the printing speed, it's about 25% of the maximum printing throughput. So we take a hurt, but it's not that bad. However, this estimation is based on more advanced optical system, meaning that we need to be able to switch the SLM pattern very quickly. So currently in our lab, we use a 60 Hertz refresh rate SLM, which is very slow, but industry have been working on a lot of more advanced system. We can also combine a DMD that is paired with SLM, so that enables us to do the switching faster. So there's still a long way in terms of next generation optical system that can be modulated faster, and also algorithms that can process faster. But in the end, the scaling law is largely similar to the relative density of the structure. So that enables us to still capture a good fraction of the throughput of the maximum throughput.
Thanks, Xiaoxing. So I have another question here. What do you view as the most significant limitations and technical challenges to overcome as you look to scale this technology?
It's a hard question. So, okay. I think just from my personal perspective, we're still we're similar to academic lab. We kind of scavenged all the motion state laser system and things that we can do to make this happen. We're at a stage where we need really lithography level tools for the controlling the laser, the motion, and those are very difficult for me to do, but I think industry can do it much better. Our system is very complex for a research lab, but it's so simple comparing to ASML's UV system. But we're at a stage where regular R&D is not sufficient. Overall, I think our system actually is quite simple, where we use an array of pixels on the SLM to control one metal lens and then control focal spot. And so that core concept is very scalable, and a lot of it will be the engineering to make a very reliable system. I think there's still a long way to go, but I think the core concept is very simple and elegant, which make it very scalable. So I don't see some fundamental physics limitation for scaling.
Thank you. Yeah, that's great. I've seen a couple of questions here which are related about getting in touch for commercial agreements. You can go ahead and send an email to me directly, or you can go to our website at ipo.llnl.gov. I think that those are really the best portals to take the initial inquiries. In terms of next question, this was a great talk. I have a small question regarding the stability of 3D printed materials at the very small nanoscales. Does it change with the material, is there any maximum applied pressure that can cause instabilities?
Yeah, great question. So there's a lot of definition for stabilities. So the two application cases I showed, one is for fusion target, the other one is for quantum computing. Those are actually pretty extreme conditions. So for fusion, for both cases, for fusion, we need to cool it down at cryogenic temperature. We need to control liquid deuterium on the inside of target with almost zero leak rate, so that for hydrogen atoms cannot leak from the capsule. And those are very stringent requirement that we have to pass a series of tests to be able to shot it underneath. So overall, the material is very high quality. So the material we print is acrylate. So, we cannot do better than intrinsic chemical physical property of acrylate. So meaning that, it will thermally decompose when your temperature is above maybe 250 C or 300 C. And the 3D printing community have been making higher temperature material, but it's still on over 300 C degree. And there will be kind of plastic deformation because the material is amorphous polymer essentially. So there are certain limitations from the acrylic PMMA, acrylic material, and in general, it's pretty high quality. At the same time, the community are also developing a lot of new resins. So this is not only for two-photon printing, but in general, photopolymerization-based printing or photoresist community are developing more and more advanced resins. For example, you can have a kind of a ceramic and polymer composite resin, so that will give you a better performance in a lot of metrics. And there's also research in terms of parallelizing the pre-ceramic resin into ceramic, so that will further give you better material property. However, generally in those processing process, you have shrinkage, you have distortions that actually you take a toll in terms of fabrication quality. So this is still ongoing research direction.
Great, thank you. Another question here for you. Do you think this method has applications in high aspect ratio semiconductor fabrication?
Right. So I definitely think so. I don't think of it as high aspect ratio. The term aspect ratio to some extent imply it's a 2D case. You're making a feature, you're drilling a hole that have depth versus the width ratio. But I think there's opportunity in that. But I also think we can create open architecture that looks similar maybe to the lattice structure we're making that can function as interconnect for packaging. But for us, it's actually, I think there's a lot of opportunity in microelectronics, but the bar is extremely high. So we're dealing with fusion, quantum. Those are fancy applications, but the industry is still new. So we can actually immediately provide benefit to the community. But for semiconductor industry, the bar is so high that it will take a very long time, a lot of investment to actually make our process or make 3D printing in general applicable, can be part of foundry workflow. And we are very excited to work on that. And I also think semiconductor industry is one of the few industries that are open to complex processes. They love challenges. So I think I really do hope our process can be there at some time.
Yeah, we love our challenges too here as well. Next question is, do the meta lenses need to be customized for different part designs, arrangements, objectives, printing resins, anything like that?
Yes. It doesn't have to, but it can benefit from that. Like say, if you have a microscope, for example, you generally have different magnification lenses for different samples. So we have been mostly using 2 meta lens, and they have different size and different array size and different lens size. But in the future, I think for a commercial system, you can either specialize in one lens, and within that one lens, we can turn focus point off. We can have different periodicity. There's a lot of things you can do, but you can also have the option of swapping a different set of lens. For example, you can go from, kind of a square grid into a hexagonal grid for some application that is more beneficial. A lot of time we actually want to reduce the resolution, so have a lower numerical capture lens so that you can print faster for larger volume. So I do think if this technique becomes a workhorse for a certain fabrication technique, probably you need to use specialized lens to basically maximize the performance.
Thanks. Another good question here. Thanks for the great presentation. Are there any limitations in the overall print height?
So in principle, no, because we have a lens array and we have a build platform. We start at the bottom of build platform, and as we print, within the print is still layer by layer. So basically, we print from the substrate and upwards. So the metal lens is kind of it's going away from, actually it's the platform is going down, going away from the metal lens, so that we can continuously adding more height into the structure. However, in the actual implementation implementation, right now we're essentially putting our resin in between the two wafers. So that's kind of give us limitation of how high we can print. But if you design a kind of a vat or design some flowing mechanism to continue supply the resin, and there's no fundamental limitation in terms of the height. But I do want to mention, because we're doing multiplexing essentially laterally in the 2D plane, so that our throughput is the fastest when we're enhancing the print area. So for the Z, we still have to build up that Z height. So that's, do take time to print Z. This is true for any 3D printing method.
All right, got another question here. Are you able to print features like the traps you showed on a substrate like glass or a silicon wafer?
Right. So for the trap I showed, we're using commercial printer, single objective printer to print for our research, and we haven't used our parallel printer to print that. And just because it's pretty hard, it's still a prototype printer in our system. In theory, I think it's definitely possible. I think the only way for 3D printing to use is to be combined with other fabrication techniques, especially in the microelectronic industry. We don't want to replace the perfect CMOS processes. Ideally, we want to be a step that we can insert into that workflow. So printing from glass substrate or substrate with vertical vias or other things is definitely, it's possible. We can do it on regular printer, but to translate into parallel printer will take some engineering effort, but it's totally possible.
Mm-hmm. Another question here on how the metal lens ray is illuminated. Is the laser still scanned, or is the SLM for mass generation? What's the flux per metal lens that works for printing, and is the power uniform across the entire array?
Mm-hmm. Yeah, this is a great question. So the motion, the 3D motion is done through the stage only. So other than the stage, everything else is stationary. Maybe in the future there could be some other motion, but our implementation right now is that everything is stationary other than the stage. So the laser is a very good question because it's actually a very practical, difficult thing to do. Is the laser itself will have a Gaussian distribution, ideally, and there will also some other variation defect in the optical beam path that give it a non-uniform distribution. And our metal lens could have defect. When you have larger rate, inevitably there will be defect. So that's why the spatial light module is actually very important in our system. We set the levels on the spatial light modulator such that the final focal spot are extremely uniform. And we do it by calibrating the printing system. But once you calibrate it, the print system can operate for a very long time. But we have to do initial calibration such that to set the SLM values on each pixel of that SLM such that each focal spot is equal intensity. Otherwise, you would see some focal spot doesn't print, some focal spot print, or some focal spot have too much power and will bubble in the liquid resin. So that spatial light model is a very important aspect. In this implementation, we lose a lot of energy, so the SLM can only throw away energy. But in the future, you can also imagine you have some flap top hat conversion to levelize the energy first, and then use SLM to do some fine tuning of the intensity.
Great. Another question here. Do you see any delamination issues or defect tendency along the edges between metal lens projection boundaries?
Yeah, if I understand it correctly, the question is because we're printing substructure with each metal lens, and then we are essentially stitching them together, but we only need to do one-step stitching. So in our design, we normally design 1 micron overlap in between each metal lens subprint. And this 1 micron overlap is enough to have very nice stitching. Previously, when I use commercial printer, I generally put in like more than 1 micron overlap to ensure that, because we have to do so many different stitchings throughout the process, especially if you have a 2D array of individual stitches. Like the first row is actually pretty well, but if you go to the second row, that motion is really large. So that stitching actually need to have a more tolerance. So I normally do at least 5 micron, 10 micron overlap in between substructures. So in our system, because we only have to do one-time stitching, so generally 1 micron overlap is sufficient to have very nice stitching property.
Right. For the pillar geometry, what's the minimum diameter possible? And what's the minimum spacing between them? What's the maximum possible aspect ratio?
Okay, so our diffraction, sorry, I didn't specify that in the presentation. So our lens have numerical aperture. The highest we do is about 1. So that gives us a kind of a radial resolution of that focus spot to be about 300 nanometer, and the axial resolution maybe about 1.5 micron. So that's the minimum diffraction limited resolution you can get very reliably. That because we have a 2 photon threshold, that threshold is actually very reliable. You can do 300 nanometer line widths quite easily. We also, in the community, we can also fine-tune the focus file very carefully to write 100 nanometer, close to 100 nanometer lines. But generally, those lines is subject to boundary conditions. So we have to design the overall structure mechanically to be very robust in order to print 100 nanometer line width, which is possible. But overall, 300 nanometer is a very reliable value. And the question is also very insightful because the diffraction limit is actually about making the gap in between the features. We haven't really did a lot of testing, but we did print like wood pile structures. I think with spacing about 2 micron, I say. But I don't have a very good exact value to give you, but on the order of I think the pitch, maybe you're asking the pitch of lines on the order of 1 to 2 micron. I think that's a minimum.
Gotcha. Another question here. What types of scaffold coatings have you attempted for your minimum print features in terms of materials properties? Can you sacrificially remove the resins to allow for more extreme impure materials?
Right. So because I deal with a lot of applications that require high quality metal, so I normally use vapor deposition. So either CVD, PVD, ALD, even ALD would be very nice because that's the only technique that we don't have line of sight issue. We can have very nice conformal 3D coating into highly complex structure, but the material choice is a little bit more limited. So for metal, we generally use just PVD processes. On top of it, you kind of have to design the structure very carefully to allow angles of very nice deposition onto the inside of a 3D structures. But ALD wouldn't have this issue. To remove the material, I haven't done it myself. It's not trivial. My colleague have done it. So they have, for James Ogdale, my colleague, they have did ALD coating on polymer printed structure and then use some chemical etching to fully remove the polymer on the inside, so you have pure ceramic scaffold left. And so in my PhD group at Caltech with Julia Greer, we also use oxygen plasma to etch away the inner cores. But oxygen plasma is going to take very long time to etch away if you have complex structure. And chemical etching is faster, but we have to really be careful about just even capillary forces, because in that case, we're making nanometers thick ALD ceramic coating, so it becomes very delicate. So etching is possible. Generally, it's more involved on the chemistry side, and it's non-trivial. It needs to be treated very carefully.
Right. We'll just do 1 or 2 more here. Maybe this is an easier question. We'll see if this is the harder or the easier one. What kind of resins are you limited to?
It's a great question. So overall, for application purpose, I'm more comfortable with acrylate-based resin. So the monomer can have any other chemical component in it. For example, we've done pots. So those are pretty much glass with acrylate bonds surrounding that little ceramic cages. But I prefer the chemical bond that is formed during photopolymerization to be acrylate. This is because the polymerization reaction of acrylate is extremely fast. That will really have good reliability and the resolution for printing. And there are, as Austin mentioned, there are photoacid, photo-base of polymerization mechanism, but generally acrylate give you the highest resolution and reliability. But monomer or oligomer can have other functional group. We've done pre-ceramic, we've done fluorinated polymer, but the chemical bond ideally is acrylate.
Great, thanks. I think we're just about at time here, so that's probably going to do it for the questions that we can address in this webinar. If you have additional questions that didn't get answered, it's not because they're not good. There's a lot of fantastic ones in here. We're happy to have a conversation with you. Please send me an email, reach out through IPO's webpage. We'd be happy to discuss how this could be a relevant application for the problems that you want to solve. So with that, I think we're going to go ahead and conclude. Thank you very much, Xiaozheng. We appreciate everyone's time attending our meeting.
All right. Thank you very much.